Good day, guys. Today, I'm going to discuss improper integrals. What is an improper integral? An integral of the form integral from a to b of f of x dx is said to be an improper integral if any of the following circumstances holds. Number one, either the lower or upper limit or both the limits of integration increase numerically without bound. Number two, the integrand f of x has an infinite discontinuity at the lower or upper limit or at a number between the limits of integration. This definition gives these two types of improper integrals. First, improper integrals with infinite integration limits. Second, improper integrals with integrands having infinite discontinuities. Improper integrals are defined in terms of limits. If the limit defining each of these improper integrals exists, that is, has a finite value, then it is said to be convergent. Otherwise, it is divergent. These two types of improper integrals lead to the following 6 cases. Case number 1, infinite upper limit of integration. If f is continuous on the interval from a to positive infinity, then this improper integral from a to positive infinity of f of x dx is equal to the limit as b approaches positive infinity of the integral from a to b of f of x dx, if this limit exists. Let us have the following examples. Evaluate the given improper integral. Number 1, we have integral from 0 to positive infinity of 2 to the negative x dx. Here, our f of x is equal to 2 to the negative x. Since this is an exponential function, it is continuous at any number. Hence, this is continuous on the interval from 0 to positive infinity. Okay, guys? Let us now compute this improper integral. This improper integral is under case 1 because the upper limit is positive infinity. So we have integral from 0 to positive infinity of 2 to the negative x dx. And this is equal to the limit as b approaches positive infinity of the integral from 0 to b of 2 to the negative x dx. Okay? So we can evaluate this by exponential integration. Here, our u is equal to negative x, and du is equal to negative dx. So to complete the du, we have to multiply by negative and then balance outside by negative. So getting limit as b approaches positive infinity of integral from 0 to b to the negative x times negative dx, and then outside of the integral sign, we have negative, okay? So giving limit as b approaches positive infinity, so this is equal to negative a to the u, so that is 2 to the negative x over ln a, that is ln 2, evaluated from 0 to b, okay? So let us now evaluate this expression when x is b. So getting limit as b approaches positive infinity of negative 2 to the negative b over ln 2 minus, since it's negative, so it is now positive, 2 to the 0 is equal to 1 over ln 2. Okay? So this time, we're going to evaluate the limit as b approaches positive infinity. For the first term, as b approaches positive infinity, 2 to the negative b approaches 0. Okay? So, and for the second term, since it is constant, so its limit is simply 1 over ln 2. So that we have 0 plus 1 over ln 2. So finally, we have 1 over ln 2. Okay? So this means that this improper integral converges because this is a finite value. It converges to 1 over ln 2. Okay? So let us have the second one. We have the integral from 5 to positive infinity of dx over square root of x minus 1. So what about this? Okay? Our integrand is 1 over square root of x minus 1. So that f of x is equal to 1 over square root of x minus 1. Okay? Now, we want to determine if this is continuous from 5 to positive infinity. Checking this function. When x is 5, we have 5 minus 1. The square root of this is 2. And if x is greater than 5, this radical is always defined. So therefore, this is what? Continuous on 5 to positive infinity. Okay? So let us now compute that improper integral. So we have integral from 5 to positive infinity of dx over square root of x minus 1, and that is equal to limit as b approaches positive infinity of the integral from 5 to b, this 1 over square root of x minus 1. When we bring this radical up, we have x minus 1 raised to negative 1/2, then dx, okay? So we will able to evaluate this integral by general power formula, no? Okay? So if we let u as x minus 1, and then its du is equal to dx, then we have integral from 5 to positive infinity of dx over square root of x minus 1 is equal to the limit as b approaches positive infinity of, so we have to put here, so we have u to the n plus 1, so that is 1/2 over 1/2, evaluated from 5 to b, okay? So let's simplify. So this is equal to limit as b approaches positive infinity of, so we have 2 times x minus 1 raised to 1/2, evaluated from 5 to b, okay? So at the upper limit, we have limit as b approaches positive infinity of 2 times, so this radical, x minus 1 raised to 1/2, so is equal to square root of b minus 1, okay? So at the lower limit, we have 5 minus 1, that is 4, is square root, so giving 2. Okay, now? So let's now evaluate this limit. As b approaches infinity, so b minus 1 gets bigger and bigger, and the root of that, the square root of that, gets bigger and bigger also. This approaches positive infinity, so hence, the limit of this is what? Positive infinity. Okay? This limit of 2 will not affect the limit of this. So this will be when subtracted from a very big number is still that big number. Okay, guys? So meaning this improper integral has no finite value. The limit does not exist. Hence, we say that the improper integral from 5 to positive infinity of dx over square root of x minus 1 is divergent. Okay? So let us have number 3. So given the improper integral from ln square root of 3 to positive infinity of e to the x dx over 1 plus e to the 2x. So here we have f of x is equal to e to the x over 1 plus e to the 2x. Okay? Now, since the denominator is never negative and the numerator is involving exponential, this type of function doesn't have any point of discontinuity. So hence, it is continuous at any number and therefore continuous on the interval from ln square root of 3 to positive infinity. Okay, guys? So this integral ln square root of 3 to positive infinity of e to the x dx over 1 plus e to the 2x is equal to limit as b approaches positive infinity of integral from ln square root of 3 to positive b, so of e to the x dx over 1 plus e to the 2x. So, and this is equal to, how do we evaluate this? We can evaluate this by using integral leading to inverse trigonometric function in particular. So integral leading to inverse tangent, okay? So here we can let u to be e to the x so that its du is equal to e to the x dx, okay? So our a here is equal to 1. So getting integral from ln square root of 3 to positive infinity of e to the x dx over 1 plus e to the 2x is equal to limit as b approaches positive infinity of, so we have 1 over 1, so that is 1 over a, 1 over 1, inverse tangent of u, which is e to the x over 1, evaluated from ln square root of 3 to positive b or to b, no? Okay? So let's evaluate this inverse tangent of e to the x when x is equal to b. So we get limit as b approaches positive infinity of tangent inverse of e to the b minus inverse tangent of e to the, so our x this time at the lower limit, we have ln is square root of 3, okay? So let's simplify this. So this is equal to limit as b approaches positive infinity of tangent inverse of e to the b minus, now from one of the properties of logarithms, if we have e to the logarithm to the base e of square root of 3, this is simply square root of 3. Hence, we have inverse tangent of square root of 3. Okay? So from here, we can now evaluate the limit of this. For the first term, as b approaches infinity, e to the b increases without bound also and approaching positive infinity. So, and as e to the b approaches positive infinity, tangent inverse of e to the b approaches what? Approaches pi over 2. Okay? So again, as e to the b approaches positive infinity, the value of this inverse tangent gets closer and closer to pi over 2. So hence, its limit is pi over 2. So for the first term, so that is equal to pi over 2, the limit of that. And for the second term, limit of this is simply inverse tangent is square root of 3 because this is constant. But inverse tangent of square root of 3 is equal to pi over 6. So that is tangent is pi over 6 is square root of 3. Hence, inverse tangent is square root of 3 is pi over 6. Okay? So simplifying, we get, so the LCD is what? The LCD is 6. So we have 3 pi here minus pi, and this is equal to 2 pi over 6, and that is pi over what? Pi over 3. Okay, guys? Since this is equal to a finite number, this limit, hence we say that the given improper integral is convergent and it converges to pi over 3. Okay? Let us have number 3. So let us have number 3. We have integral from 0 to So let us have number 3. We have integral from e to positive infinity of dx over x ln of x. Okay? So here our integrand is 1 over x ln x. It has a problem when x is 0. So, but when x is greater than 0, so the denominator will not be, so when x, this is okay when x is greater than 0, okay? So when x is greater than 0, except when x is equal to 1, this is what? Continuous, okay? So hence, since we are just after from e to positive infinity, so it has no problem with those values. So this function is what? Continuous on the interval from e to positive infinity. Okay? So we can proceed. So integral from e to positive infinity of dx over x ln x, and that is equal to the limit as b approaches positive infinity of integral from e to b of dx over x ln x. So how do we evaluate this integral? So we can apply integral of du over u. So it is equal to limit as b approaches positive infinity of the integral from e to b. We can put this x in the numerator, getting 1 over x, then multiplied by dx over ln x. So I can take my u as what? ln x, and its du is equal to dx over x, which is the numerator. So therefore, this is equal to the limit as b approaches positive infinity, and this is equal to what? Integral of du over u, du over u. So we have ln of x. So no need for absolute value here because ln e is positive and also positive for x greater than e. Okay? So we now have from e to b. Okay? And so we have limit as b approaches positive infinity. Applying the upper limit, we get ln of ln b, and then minus ln of ln e. But ln e is what? ln e is equal to 1. So we can write here limit as b approaches infinity of ln b minus, this is 1, and ln 1 is what? Is equal to 0. So this is equal to 0. So getting limit as b approaches positive infinity of simply ln of ln b. Okay? So as b approaches positive infinity, ln b approaches positive infinity. So meaning ln keeps on growing also. Okay? And if ln b keeps growing, the value of that keeps growing also. So ln of ln b approaches positive infinity also. Okay? So therefore, this limit is equal to positive infinity, meaning this limit does not exist. Hence, we say that this integral, this improper integral, is divergent. Therefore, integral from e to positive infinity of dx over x ln x diverges. Okay? Or it is a divergent integral. Okay, guys? So let us have the fourth one. Number 4. I think this is the fifth. So this is the fourth one. So let me correct the numbering. And this is the fifth one. Okay? Integral from one to positive infinity of dx over x multiplied to 1 plus x. Okay? So here our f of x is equal to 1 over x plus 1. Okay? Now this function is continuous on the interval 1 to positive infinity, because the problem is at what? Is at -1 and at 0, which is not inside this interval. Okay? And for the rest of the values, from 1 to positive infinity, so this function is continuous from that number. So let's now proceed. We have integral from 1 to positive infinity of dx over x times x plus 1 or 1 plus x, and that is equal to the limit as b approaches positive infinity of integral from 1 to b of dx over x plus 1. Okay? We can evaluate this using integration by partial fractions. So by partial fraction decomposition, we have 1 over x plus 1. So this is equal to a over the first factor in the denominator is x, then plus b over the second factor, which is linear also, x plus 1. This is under case 1 in the partial fraction decomposition. So to solve for a, we have when x is 0, but we have to remove x here. So that is 1 over x plus 1 evaluated when x is equal to 0. And this is equal to 1 over 0 plus 1, so getting 1. Okay? What about b? b is equal to when x is what? When x is -1. So we have to remove x plus 1 here. So we have 1 over x evaluated at x equals -1. And this is equal to 1 over -1, getting -1. Okay? So therefore, the improper integral from 1 to positive infinity of dx over x plus 1 is equal to limit as b approaches positive infinity of integral from 1 to b of 1 over x minus 1 over x plus 1. Okay? Quantity dx. So this is equal to limit as b approaches positive infinity. So this integral is equal to what? ln of x. No need for absolute value because x is always positive in the given interval. So we have minus ln of x plus 1, same thing. No need for absolute value because x plus 1 is always positive on the interval 1 to positive infinity. So evaluated from 1 to b. So this is equal to limit as b approaches positive infinity. At the upper limit, this is equal to what, guys? ln b minus ln of b plus 1. Okay? Minus, this is ln 1, then plus negative here, negative ln, 1 plus 1 is ln 2. Okay? So simplifying this, we get limit as b approaches positive infinity of ln b minus ln of b plus 1, then minus ln 1 is 0, so minus minus, so this is now plus ln 2. Okay? Now, as b approaches infinity, ln b approaches infinity also, and ln of b plus 1 approaches positive infinity also. So it means we have infinity minus infinity type of indeterminate form, okay? Okay, guys? So hence, we say that this limit, we have to express it in the form of what? Of either 0 over 0 or infinity over infinity. So how? So we now have dx over x, x plus 1, and that is equal to we have limit as b approaches positive infinity. Let's combine these two logarithms. We have ln of b over b plus 1 plus ln of 2. Okay? Now, for the limit of ln of b over b plus 1, we have limit as b approaches positive infinity of ln of b over b plus 1. This is equal to ln of limit as b approaches positive infinity of b over b plus 1. And this is equal to ln of, so here, this is approaching positive infinity. This approaches also positive infinity. Hence, we have infinity over infinity form. And then we can apply here L'Hopital's rule. So getting the derivative of b, that is 1. So with respect to b, derivative of b plus 1 with respect to b is also 1. Okay? So it means we have ln of what? Ln of 1. And ln of 1 is equal to what? 0. Therefore, the integral from 1 to positive infinity of dx over x plus 1 is equal to, so for the limit of the first term, we have 0. And then second term, we have ln 2. Okay? So getting ln 2. So it means this improper integral converges because we get a finite value. It converges to what? ln 2. Okay, guys? Another case of improper integral, we have a case where at the lower limit, we have infinite lower limit of integration. If f is continuous on the interval negative infinity to b, then the improper integral negative infinity to b of f of x dx is defined by the limit as a approaches positive infinity of the integral from a to b of f of x dx, if this limit exists, okay? So let us have the following examples. Evaluate the improper integral negative infinity to 1 of x minus 1 multiplied to e to the x dx. Okay? So here our f of x is equal to x minus 1 e to the x. Since the involved functions here, algebraic, which is a polynomial, and exponential, and these two types of functions are continuous anywhere. Hence, it is continuous on the interval negative infinity to 1. Okay? So we can now proceed. So this improper integral is under case 2 because we have a lower limit that is negative infinity. And we can define this as what? As limit as a approaches negative infinity of the integral from a to 1 of x minus 1 multiplied to e to the x, then dx. Okay? Now, to evaluate this improper integral, this integral here, we can apply integration by what? By parts. Okay? So here, we have u is equal to x minus 1 and dv is equal to e to the x dx. Okay? So that du is equal to dx while v is e to the x. So getting integral from negative infinity to 1 of x minus 1 e to the x dx, and this is equal to the limit as a approaches negative infinity of, so we have here x minus 1 multiplied to e to the x evaluated from a to 1 minus the integral from a to 1 of e to the x dx. Okay? So this is equal to limit as a approaches negative infinity of x minus 1 e to the x, and this is equal to negative e to the x evaluated from a to 1. Okay? So let us evaluate this at the upper limit. So we have limit as a approaches negative infinity of 1 minus 1 is 0 times e to the first. So we have 0 minus e to the first, then minus, when x is equal to a, we get x, so that is a minus 1 e to the a minus e to the a. Okay? So let's simplify this. We get limit as a approaches negative infinity of, this is negative e minus, I can factor out e to the a here. So we have e to the a times, we have a minus 1 getting a minus 2. Okay? So that this is equal to So what is the limit of this? As a approaches negative infinity, this is simply e to the e, because as a approaches negative infinity, this is simply negative e, because this is constant. So what about this? Now, as a becomes big negative, this is going to be 0, and this is going to be negative infinity. Okay, so again, this is going to be negative infinity, and this is going to be what? Going to be 0. Therefore, we have what? We have 0 times infinity type of indeterminate form. Okay, so let's evaluate this limit. We have limit as a approaches negative infinity of e to the a minus 2. So this is equal to the limit as a approaches negative infinity. So we have a minus 2 over e to the negative a. So I rewrote this in terms of a minus 2 over e to the negative a, so that I can come up with negative infinity over, this is going to be positive infinity, getting what? Getting infinity over infinity type of indeterminate form. Okay? So by L'Hopital's rule, the derivative of the numerator is what? Is 1. The denominator, we have negative e to the negative a. So the derivative with respect to a. So as a approaches negative infinity, and the limit now of this now exists, and it is equal to what? So this approaches negative infinity. Okay? E to the negative a, as a approaches negative infinity, this is going to be positive infinity. This is negative, so negative infinity. So 1 over a very big number is going to be what? Going to be 0. Okay? So this is simply 0. Hence, we have what limit? We have the limit simply negative e. Okay? So we have integral from negative infinity to 1 of x minus 1 e to the x dx is equal to what? Negative e minus 0, so that we have what? We have equal to negative e. Okay? So since this is finite, we say that this improper integral converges, and it converges to what? To negative e. Is that clear, guys? So let us have number 2. Integral from negative infinity to positive 2 of x dx over 1 plus x squared. So here, we can take f of x as x over 1 plus x squared. This is continuous on negative infinity to positive infinity. Therefore, it is continuous on its any subset. So, continuous on negative infinity to positive 2. So we can now proceed. Integral from negative infinity to 2 of x dx over 1 plus x squared is equal to limit as a approaches negative infinity of what? of integral from a, so to 2, and then we have x dx over 1 plus x squared. Okay? So how do we evaluate this integral? So this can be evaluated by integral of du over u. So our u here is what? 1 plus x squared. What about du? So we have 2x dx. So from here, we now have limit as a approaches negative infinity. I'm going to put 2 here. And then balance outside by 1/2. So getting ln, getting limit as a approaches negative infinity of 1/2 of ln of 1 plus x squared. No need for absolute value because this is always positive for any real number. So evaluated from a to 2, okay? So that is equal to limit as a approaches negative infinity of 1/2. At the upper limit, we have ln of 1 plus 2 squared, that is 4. So minus 1/2 of, at the lower limit, we have ln of 1 plus a squared, okay? So let's simplify. Limit as a approaches negative infinity, this is equal to 1/2 of ln 5 minus 1/2 of ln of 1 plus a squared. Now, as a approaches negative infinity, ln of 1 plus a squared approaches what? Approaches positive infinity. Therefore, this is going to be what? Going to be negative infinity. So, and then 1/2 plus 1/2 ln 5 minus a very big number. So that is equal to a very big number, negative. So we have negative infinity, okay? So this means that this integral is a divergent integral. So again, the integral from negative infinity to positive 2 of x dx over 1 plus x squared is equal to what? Is equal to negative infinity, which means it is not a finite number since the limit does not exist, or that is negative infinity. So hence, this is said to be divergent integral, okay? So again, this integral is divergent. Okay? So let us have number 3. We have integral from negative infinity to 0 of dx over 2x minus 1 quantity cubed. So here in this improper integral, f of x is equal to 1 over 2x minus 1. Okay? So there is only one point of discontinuity here. It is at x equals 1/2. So since 1/2 is not in this interval, so this is continuous for sure on negative infinity to 0. Okay? So let's now compute this integral. So this integral is defined by the limit, no? So we have limit as a approaches negative infinity of the integral from a to 0. So 1 over 2x minus 1 quantity cube, that is the same as 2x minus 3 quantity 2x minus 1 rather to the negative 3 dx. Okay? So we can evaluate this using what? General power formula. Okay? So our u is equal to 2x minus 1. Du is equal to 2 dx, so that the integral from negative infinity to 0 of dx over 2x minus 1 quantity cubed is equal to the limit as a approaches negative infinity of integral from a to 0. I'm going to put 2 inside, balance outside by 1/2 to get inside 2x minus 1 quantity to the negative 3 times 2, then dx. Okay? So this is now equal to limit as a approaches negative infinity of 1/2 times, so by general power formula, this is u to the n plus 1 over n plus 1 evaluated from a to 0. Okay? So that is equal to the limit as a approaches negative infinity. So here we have 1/4. So that is negative 1/4 times what? 1 over 2x minus 1 quantity is squared. Evaluated a to 0. Okay? So at the upper limit, this different, at the upper limit, we have this expression is equal to negative 1/4. So this is 0. Square it here. So minus 1 quantity squared is 1. 1 over 1. So we have negative 1/4 minus negative. So it is now plus 1/4 times 1 over 2a minus 1 raised to 2. Okay? As a becomes large negative, then when you square it, it is large positive. 1 over a very big number. So this is going to be what? Going to be 0. Okay? So getting 1/4 plus 1/4 times going to be 0. Therefore, this is all equal to what? Negative 1/4. Okay? So this means this integral is a convergent integral. It converges to negative 1/4. So let us have the last one. We have number 4, integral from negative infinity to 0 of e to the x dx over 3 minus 2 e to the x. Okay? So here, what is our f of x? Our f of x is e to the x over 3 minus 2 e to the x. Okay? the only point of discontinuity here is when x is what? When x is ln, I think ln, if I'm going to equate that to 0, we have negative 2e to the x is equal to negative 3. E to the x therefore is equal to 3 over 2. So x is ln of 3 over 2. Okay? So the only point of discontinuity here is when x is what? When x ln 3 over 2, which is not inside this what? This interval. Therefore, this is what? This is continuous on the interval negative infinity to 0. Okay? So hence, we cannot proceed. So negative infinity, integral from negative infinity to 0 of e to the x dx over 3 minus 2 e to the x, and that is equal to the limit as a approaches negative infinity of integral from a to 0 of e to the x dx over 3 minus 2 e to the x. Okay? So here our u is equal to what? 3 minus 2 e to the x. Du is equal to negative 2 e to the x dx. So we can have it integral of du over u. So getting limit as a approaches negative infinity, I will put negative 2 balanced by negative 1/2 to get what? ln of 3 minus 2 e to the x. Okay? Now, in this case, do we need absolute value, guys? Here, do we need absolute value? So I think we don't need absolute value because e to the x, when x is negative, so times 2, this is always less than 3. Okay? So evaluated from a to 0. So limit as a approaches negative infinity of negative 1/2 of, at the upper limit, we have ln 3 minus 2 e to the 0. E to the 0 is 1. So getting 3 minus 2 times 1 here. Okay? And then minus, so we have 1/2, positive now, ln of 3 minus 2 e to the a. Okay? And this is equal to getting limit as a approaches negative infinity. So let's simplify this. Negative 1/2 ln of 1. But ln 1 is what? Equal to 0. So this is equal to 0. Then plus 1/2 of ln of 3 minus 2 e to the a. So evaluating now the limit. So as a becomes large, negative, e to the negative large is going to be what? It's going to be 0. Okay? So hence, this is approaching 1/2 ln 3. Now, since this is finite, so we say that this integral converges, and it converges to 1/2 ln 3. Any question, guys? That's it. So that's for case 2. We're going to continue this discussion in the next video, discussing cases 3, 4, 5, and 6. That's all for today, guys, and have a nice day.